Hey everyone, it's Dr. Calkins. This time we're doing experiment 18. Time to use your head of cabbage. So in this lab we're going to talk a little bit about acids and bases first, practice some acids and bases, talk about where you can find or recognize acids and bases, and then we're going to do some hands-on testing of household products at the very end. So as we talk about acids and bases in class, there are two major categories that we talk about in our textbook, and the first one is Arrhenius. He was the first person that came up with this idea of ions. Sadly, it was well before protons, neutrons, electrons were discovered, so there's a lot of history behind that development of acids and bases. But he was the first one to call an acid an acid. And in his definition, to be an acid, you have to produce H+, the hydrogen ion. Uniquely, the H+ ion will react with water, forming hydronium, one of the few ions in your ion list that we haven't used up until now. To be a monoprotic acid, we need to know what mono means first, which is one. Then we need to know what protic means. Think about protic, that means proton. And if we look at the periodic table, the only atom with one proton is H+. So oftentimes we call H+ the proton, because if hydrogen has one proton, has one electron, but loses its electron to become a positive cation, the only thing left is just a proton. So when we say monoprotic, what we're really just saying is one H+, or in this case one hydronium when it reacts with water. So diprotic would now be two H+, or two hydroniums when it reacts with water. Triprotic being three. And in a different lecture we'll show you several examples of those. To be an Arrhenius base, because Arrhenius was dealing with water, if we have H+, then we should also have OH negative. And this tells us that water can separate into two pieces, H+ and OH negative. So again, monoprotic would be one H+, two H+s for diprotic, three H+s for triprotic. Lots of monoprotics, several diprotics, very few triprotics that we'll learn in class. The Arrhenius base, though, is a hydroxide, and hydroxide is determined by the metal cation. So obviously, if you're in group 1, you're a +1, you're only going to be able to handle one hydroxide because it's negative and this group is +1. So that's a perfect match. If you're group 2, though, you can hold two hydroxides, so it's a very similar process up here, 1 versus 2 versus 3. But hydroxides, it's +1 versus +2, and then maybe aluminum to +3 or whatever. But it's the metal that determines hydroxides here, where it's the ion that hydrogen is attached to up there that determines the H+. So this was the first definition, and much like the first telephone, things change over time and new ideas and new theories about acids and bases come along. And the next theory that came along was down here with Bronsted and Lowry. So Bronsted and Lowry tried to take away this generic definition of H+ and OH negative. They were the first group to realize that you didn't have to be hydroxide to be a base. There's other things that can be bases, like ammonia. Ammonia can become ammonium. We saw that in our chromatography experiments with that white dust. So Bronsted and Lowry are just saying, let's open the floodgates on what it could be to be a base. So let's just talk about H+ and where H+ goes. So Bronsted and Lowry acids are going to be H+ donors, just like being a kidney donor. You would give a kidney to somebody else. Bronsted and Lowry acids will give an H+ to somebody else. So if somebody gives H+, then somebody needs to accept H+, and those are bases. And oftentimes you can think of hydroxide accepting an H+ to become water. But now we can also see that other things like ammonia and H3 can take H+ and become ammonia. So really you can imagine that this was just a generic definition with Arrhenius up top. But now when we get to Bronsted and Lowry bases, they're basically just saying there's more options. And unfortunately, Bronsted and Lowry said the only acid possible was H+. So the one that our book doesn't talk about, I'll mention briefly, is Lewis. Lewis, the same person that gave us Lewis dot structures, he went one step further and said, don't even categorize the acids so specifically. It's really about the electrons. So if you're an H+ donor, that means this plus is getting, or at least interacting with electrons, so it's really about the electrons that matter. So in a Lewis acid-base sense, it's all about the electron pairs. If you're a Lewis acid, which is not in this list and not in our textbook, you would be an electron pair acceptor, and a Lewis base would be an electron pair donor. So those are things you would see in Gen Chem, not so much in Intro Chem. But it is worth a shout out because we have talked about Lewis before. So as we move down to the bottom, we're going to use some of these definitions that we just covered and a little bit of busy work to give us practice on what we're going to see in the homework and the exam. So again, acids, bases, who's who, also in generic and more specific terms, and then again determining numbers that we have. So let's try some of that practice now. So in order to do this, we need to walk through that example first. HCl, if you think about how it's connected, here we have H and Cl. And what's important about that is notice hydrogen, H plus, and Cl negative make something that we would have called hydrochloric acid before. Now we're just being more specific in a later chapter in the book and talking about why we called it an acid in the first place. The reason we call it an acid in Arrhenius' definition is because it does have H plus in its formula. That's half of its formula. We wouldn't consider it an Arrhenius base because specifically you have to be hydroxide and there's no oxygen to be found. Bronsted and Lowry acids say that you have to be an H plus donor. Well, we have an H plus and we definitely can donate it. HCl is a very strong acid. Eats through cement off of bricks. To be a Bronsted Lowry base, you have to be able to accept more H's, and unfortunately Cl is a negative one. It can only hold one. So it can't accept any more H's whatsoever. We would call it a monoprotic acid because it only has one hydrogen. We wouldn't talk about hydroxides at all. That wouldn't apply, and that's because there's no hydroxides in its formula. So HCl used in a lot of toilet bowl cleaners, something that's used in a lot of drain cleaners is sodium hydroxide. So you gotta be careful on this one. Sodium has a partner called hydroxide. So even though it says H in the formula, you have to be able to release H plus, and hydroxide can't. So in this situation, because we can't, we would just say no. Can't be an Arrhenius acid because it has an OH negative. So no H plus to lose. Can it be an Arrhenius base? Does it have hydroxide? We would say sure. It has one hydroxide, and that's the criteria for being sodium hydroxide. So it's kind of a no-brainer there. If it's called sodium hydroxide, you'd expect a hydroxide and not the reverse. If we go to a Bronsted Lowry acid, we have to say, can it be an H plus donor? Well, it does have an H, but again, that's tied up in hydroxide, so it's not going to be released. So it's not going to be a donor. So again, that's a no. And almost everything's going to be a no, either one category, acid-acid or base-base. Only hybrids like water can do things both, and you'll see that at the bottom. Bronsted Lowry base says, are you a proton acceptor? Up above. To be a proton acceptor, that would mean hydroxide would accept an H and become water, and that works. So definitely a yes there. So we have a yes for both definitions, and that's because we are hydroxide and we do have the ability to accept H's. We just don't have the ability to donate them, and definitely don't have the ability to release them into solution. So definitely this one doesn't count because we don't have hydrogens that can be released or donated. But because we're group 1 for sodium, we're going to have one hydroxide. And that's because sodium is a positive 1 cation. Let's do one more and then we'll let you try the rest on your own. So again, think about how this separates. This 2 would have came from sulfate. This would be imaginary 1 past sulfate. So does it have H plus in its formula? Sure it does. It has 2 H positives in its formula. That also tells us already that it's going to be diprotic because it has 2 H's. Does it have any OH's? Well, no, it's got a sulfate. No OH's. Can it be an H plus donor? Yes, it can. Donates 2 H plus ions. And can it accept any more H's? Well, sulfate can only hold 2, and it already had 2, so again, no. So almost always you're going to see no and no for base definitions, just like no and no for acid definitions as you see those. Again, it doesn't have a hydroxide, so that does not apply. So I'll give you a few minutes to pause the video and you can try the rest. Eventually you'll be able to check the answers. Alright, so looking at page 120, a few more things before we get to lab. Remember that acids taste sour. Your tongue is great at that by recognizing sour as your taste buds on the sides of your tongue. So if you ever taste a lemon, your cheeks pucker, that's because your tongue is contracting on the edges. Just like bases are bitter, and that's because the back of your tongue, towards the back of your throat, those are bitter, and that's a good defense mechanism for your stomach because it'll give you the gag reflex if you eat something very basic. And that's good because the first place all that base is going to go is to your stomach. Try to neutralize it, and that'll give you an upset stomach. So your tongue is a great acid-base identifier for that reason. But another good identifier is paper. And where does paper come from? What's important about paper is plants come from, or at least they produce paper, and plants change color based on acids and bases. So much like our tongue, plants respond to that H plus or OH negative kind of ion. It's also true that acids react with metals and produce hydrogen gas. We'll see that in another lab coming up, as well as several labs previous to this. And bases are going to be very slippery like all of our soaps. So let's look at some household products. These are many of the ones we're about to test in lab coming up. So notice as H plus goes up, hydroxide goes down. Let's zoom out and try to see all of this at once. So notice the scale. As this gets tinier and tinier and tinier and tinier, the base goes larger and larger and larger and larger, and vice versa. The pH scale that we'll talk about and have been talking about, and we also have it in our previous lab, that's a acid-related scale. So notice the power of 10 and the pH are the same. Let's take that negative way, and that's where we get that pH idea. Definitely a low pH is very acidic, so there's our stomach acid. Lemon juice has got that citric acid, very acidic, and things that are also very sour, very acidic, so grapefruit juice, beers, wines, colas, coffees, a lot of things that are bad for your teeth. Your dentist doesn't like you to drink a lot of these ideas because they dissolve the enamel on your teeth. Rainwater, very acidic because it dissolves carbon dioxide to make carbonic acid. Urine, slightly acidic, but it is basic enough with the ammonia in there that it's good for those very strong acids in jellyfish stings and things like that. Milk getting closer to neutral, we get to pure water. Human blood's about 7.25, 7.35. Baking soda, bake it, it produces carbon dioxide from those carbonates that are so basic, the same kind of thing that's in a lot of antacid, like Tums and Rolaids. Also with a little bit of magnesia in there to help loosen up things down south. And then eventually we have things that are slippery like bleach and ammonia, and then even oven cleaners and drain cleaners that are extremely basic because they're way down there in those high pH kinds of numbers. So as we get ready for lab, we're going to be using our colored pencils, and we're going to be using purple cabbage as a great indicator for recognizing pH. So we're going to use pH paper to prove that cabbage juice is just as accurate because they're both plants and they both can recognize acids and bases. So we'll give you a few minutes to find some colored pencils because we're going to need them in this next section. Alright, so we're going to have a 400 ml beaker. We're going to put it full, at least half full, of dime-sized pieces of cabbage. And then we're going to put enough distilled water in there to get us up to about 200 mils. Then we're going to have to boil it for probably 10 to 20 minutes to get that dark purple color. So here's our cabbage. Notice it's nice and purple. And then on the back side, really purple, and that's the kind of stuff that we want. This dye in these leaves, those are the ones that are so responsive to pH, more so than these ones on the outside. So we're going to start tearing some of these pieces off and put them into our beaker of water. So dime size, smaller the pieces the better. They'll be a little faster at getting that dye color out. So as we do this for quite a while, we're going to get a lot of that dye to disperse. You can probably starting to see that it's tinting the water already. And we'll do this for a few more minutes and then we'll come back. Alright, while things are boiling, we're going to take 15 test tubes. We're going to put in pH 0 all the way to pH 14. We have these bottles already. So starting at 0 all the way across down to 7, this is neutral. Everything back this way is acidic. And then we take this way towards our strongest base there at 14. So we're going to fill these about half the peg or so in order, and then we'll be right back. All right, so we've added about half a peg or so of each of our solutions, about 2 milliliters. And notice they're all still clear. Nothing too exciting yet, but this is our most acidic here, neutral being in the middle, and then our 14 being way over here. So 0, about 7, about 14. And now we're gonna go wait for our cabbage to cook. All right, so our cabbage is off to the races. We're going to let it cook a little while longer, but we're definitely getting some of that purple color that we want. It's really not done until we start seeing those leaves start to get a little paler. So we're gonna let it keep going for quite a while. So in the meantime, we're going to test the pH of household products, first with pH paper, and then eventually with cabbage juice. So we have our 12 test tubes lined up over here. And here's our items. We're gonna be testing vinegar, and then ammonia, lemon juice, apple juice, shampoo, detergent, conditioner, mouthwash, antacids, aspirins, bleach, and then Drano. So it should follow what we see on the next page. We're going to go ahead and add those now. All right, so we had a chance to fill our tubes. Notice pretty much all of them are clear except for our juices. So we'll have to take that into consideration as we go on to our next step. All right, since our cabbage juice is still cooking, we're going to go ahead and jump ahead and start to use pH paper. We'll have time to test the actual pH paper against all of our household items and be able to color in one of our charts on the next page. All right, on page 122, we're going to do this third chart. Notice it says with pH paper, so this is where our colored pencils come in handy. We're going to color the actual colors, and then we're going to use this pH chart specific to our paper and write in those numbers. So we're going to do this one at a time. I'm just going to lay the paper itself on the handout, and then we'll give you a minute to recognize the color, and then also think about who it matches. So here's our first one, vinegar. See if you can find a match, record the number, and color it in. I'm just going to lay it there for vinegar. Our next one, ammonia. This one's a little tricky because ammonia is a gas molecule, and gas molecules tend to evaporate. And if they evaporate, they're going to lose some of their color. So notice this one early, because if you don't, it's likely to disappear here in a few minutes. So recognize which number it most likely matches, and then record it at the bottom as well as color it in. All right, on to lemon juice. Lemon juice, very sour, so we might expect this result. Here we have something in that region there, so find one that matches and record it, but also color it in with your colored pencils. Next is apple juice. So again, apple juice already has a color, but the color that the paper turns is what we want. So apple juice not near as sour. So notice the result there. Think about which number best describes it. Record at the bottom, but also color it in. Next we have shampoo. We don't want shampoo to be too strong in either direction because we don't want it to dissolve our hair. So again, recognize where it may fit and record the number as well as color it in. Notice our ammonia is starting to fade a little bit. Next is detergent. Detergent, very slippery. So recognize the number that matches there. Record it and color it in. Conditioner. Also, we don't want this to be too
crazy in one direction or the other because we don't want it to dissolve our hair. So again, recognize the color that matches and color it in and record its number. Mouthwash. So again, here's mouthwash. Recognize its most similar number, color it in. An antacid kind of gives away the name. If you have an upset tummy, this is something that could help. And that's an antacid. Something that can be on the opposite side of the scale of acid so that it can counteract it and help out. Notice our ammonia fading away quickly now. Aspirin, let's move this guy over. Aspirin is here. If you look at its structure and some of our extra credit, you probably predict that. Again, I already dropped it, but try to find a match to its number. The next one is bleach. You got to be very quick on this one. So I'm going to bring it over here because it's going to do what bleach does. So again, dip it in. Notice it already disappeared. So dip it in, already disappeared. So is that initial color that we wanted? Let's turn our paper over one more time, but you got to be quick because it does what bleach does and disappears the color. So notice that real dark green color before it disappeared, and now it's fading to clear, doing what bleach does. So I wouldn't record what you just saw. I would record what you immediately saw, and that was something way down here in that range because bleach is very slippery. So that's a tricky one because it is so fast. And then lastly, Drano. Very slippery. So record its number and its color. And other than bleach, if we pan across, there's one more shot at them. Notice we're starting to fade with ammonia like we said we would. And we'll come back with our cabbage juice. Alright, so our juice is done. Cool it down a little bit, so now we just need to pour it. And notice the color that we got. Nice dark purple color. Very indicative of the pigment that was in those leaves. So we're going to let that cool a little bit and then we'll be right back. Alright, so here's our cabbage juice. Still a little warm, so we might get some random tie-dyeing of our paper. What we're looking for here is to complete our top chart. So our top chart here is going to show us that 0 to 14 range. Very similar to pH paper, this is going to be the 0 to 14 range specific to our cabbage juice because these are already predetermined buffers from the very beginning. So let's do this, and then you'll be coloring in each little box based on the colors that you're about to see. So here's our first one. This would be 0. So record it. And here's number 1. Record it. Again, these are the ones you're coloring in. That was 2. Here's 3. 4. 5. Notice we're getting very close to neutral, so we should be getting very close to the actual cabbage color itself. 6. 7. 8. 9. 10. 11. Getting down to those strong bases. 12. 13. And 14. So take a minute to look at your colors and color in this rainbow. And I'll give you that time to do that now. All right, so now we're filling out our last chart. This is the household products that we already kind of know based on pH paper, because this would be colored in already. But now we're looking at how accurate was our cabbage juice. So now we're going to add our cabbage juice to our 12, and then now use our color chart from the pinks that are very acidic to the purples to these greens to these yellows, and see who matches by number. So not only are we going to color these in by the color that the tubes form, we're also going to look at these pH numbers matching our 0 all the way to our 14. So think number and color as we get to the next step. All right, our first one is vinegar. So we're going to take vinegar based on the color it changed and take it over here and give you a moment to think which one it best represents. You're also going to color this color, but also give it its number. So we're going to go to the next one. This next one is ammonia. This one does tend to disappear a little bit because ammonia is evaporating. Notice the color. Just be mindful of it as it tries to disappear. So again, before it disappears, color it in. Starting to fade a little bit already, but color it in. Think of this region here. And again, you can match those colors at the top chart because that's already colored in. Lemon juice is already pre-colored, but we're about to give it cabbage juice for a new color. So let's take this one and bring it across. Find a match. So again, think about those colors and numbers that represent these. Should be close to what we had with pH paper, proving that plants are very similar, but maybe slightly different in their color. So here's our apple juice. Remember, it was already pre-colored, so that makes it a little bit more difficult to think about. But again, let's take it across. Think about those colors that it's matching and record its color and its number based on cabbage juice. After apple juice, we have shampoo. So let's take it over. Again, we don't want it to be too far one direction or the other, so it should be somewhere in the middle so it's safe for our hair. So again, have a chance to color it in, but also think of its number, its pH. After shampoo is detergent, so very slippery stuff. So let's take it across. Doesn't take much to find it in that kind of range. So color it and record its number. After detergent is hair conditioner. A little thicker solution so it doesn't go quite all the way down the tube. Again, very pretty color. So again, try to think of those colors that it matches most similar to. Record the color, but also its number for its pH. Remember, pH is below 7 acidic and above is basic. Next should be mouthwash. So let's take this one across, find a match, and think of its number. Good thing about YouTube is you can always pause the video and count test tubes if you have to. We have an antacid next, so here's our Rolaids and Tums. Again, they're doing the opposite of an acid, so they should be on that opposite spectrum. So again, color and number there. Next is aspirin. A lot of times aspirin is hard on the stomach, and we're about to see why. You may even be able to buy bufferin so that it's not so strong, but definitely getting down there where it could have some irritation to the stomach. And we have bleach, so watch this one quickly because it will disappear. So notice it has a green tinge, but it goes yellow. We're probably not going to get it over there quick enough, but we do have that tinge of yellow. So again, look for that. And then lastly we have Drano. Very thick solution also. And one last one here to check, and we just have a little few questions at the bottom to deal with. Alright, so a few things to wrap up. Take your two pHs, take the average, and circle acidic or basic. Do that all the way across. Just remember, acidic is less than 7, basic is above 7. If you have a number that averages above or below 7, just round up or down as needed. Down here we say that vinegar is 5% acetic acid, so here's the picture of acetic acid. When you look at it, there's lots of hydrogens. Which one is the acidic hydrogen? Is it the one on the hydrocarbon or the one on the functional group that we should know from a previous chapter? Lastly, calcium carbonate. Which definition would apply to this molecule? Would it be a proton donor, proton acceptor? Would it have hydroxide or H+? Answer those questions and this lab is done.